Let us start with the nucleophilic addition reactions of aldehyde and ketones. As we know, aldehyde and ketones, they both are carbonyl compounds, and the carbonyl group is unsaturated but polar. And as a result, the nucleophile attacks to the carbonyl carbon and gives a addition product. And aldehydes, due to less crowding, are more reactive towards nucleophilic addition as compared to ketones. Now this is our carbonyl group. This is our reagent containing electrophile and the nucleophile, and the electrophile adds to carbonyl oxygen and the nucleophile adds to carbonyl carbon, and this product is called addition product. This is called addition product, and the first reaction which we will discuss is the reaction with the hydrogen cyanide. And this hydrogen cyanide is also called hydrocyanic acid. Hydrocyanic acid is a very weak acid, so the reaction requires the presence of some strong base as a catalyst. And this strong base helps in the formation of a nucleophile Cn-. Now this is OH-, a strong base, so it helps in the formation of a nucleophile Cn-. And this Cn- then attacks at the carbonyl carbon. Now this is our carbonyl carbon. And the second step is the protonation of this negatively charged oxygen using acidic medium. So this is our final product, and this final product is called cyanohydrin. So in one step also we can write the reaction. Now this is our carbonyl group, maybe aldehyde, maybe ketone. On reaction with the hydrogen cyanide in alkaline medium, it gives a cyanohydrin in which the hydrogen adds to carbonyl oxygen and the Cn- as a nucleophile adds to the carbonyl carbon. And since this is an example of a nucleophilic addition, aldehydes in general are more reactive than ketones. Now the first example is this. This is called formaldehyde, and when you react this formaldehyde with hydrogen cyanide in alkaline medium, it gives this addition product, and this addition product is called formaldehyde cyanohydrin. And once you have a Cn group present, this Cn is used as a synthetic intermediate, and as you know, cyanide can be changed into number of other functional groups like carboxylic acid, amines, like this. For example, this. On hydrolysis in acidic medium, the Cn group can be changed into carboxylic acid. And if you are using a reduction with a metal hydride, for example lithium aluminum hydride, this cyanide group can be changed into a primary amine. This is called primary amine. Now we take one more example. This is called ethanol. Now when we react ethanol with hydrogen cyanide in alkaline medium, it gives a cyanohydrin. This is called cyanohydrin, and this cyanohydrin on hydrolysis gives 2-hydroxypropanoic acid. This is called 2-hydroxypropanoic acid. And this acid has a common name called lactic acid. So by using this cyanohydrin formation, we can convert ethanol into 2-hydroxypropanoic acid, or we can write acetaldehyde into lactic acid. Now next example is this. This is called benzaldehyde. Benzaldehyde also reacts with hydrogen cyanide. This is called benzaldehyde. So on reaction with hydrogen cyanide in alkaline medium, it gives this cyanohydrin. And this cyanohydrin has a common name called mandelonitrile. Now ketones are less reactive towards hydrogen cyanide. So there are a number of questions we can frame. We can write conversion like ethanol into lactic acid. We can frame a question based on the mechanism, and we can also frame a reasoning question. For example, this. These are the two ketones given to you. One is called cyclohexanone. Now cyclohexanone on reaction with hydrogen cyanide in alkaline medium, it forms a cyanohydrin. This is cyanohydrin. But if you are taking this ketone 2,2,6 trimethyl cyclohexanone, it does not form any cyanohydrin on reaction with hydrogen cyanide. It does not form any cyanohydrin. The reason is that ketone is highly crowded. In this case, the ketone carbon is highly crowded due to the presence of 3 methyl groups. So difficult for a cyanide to attack, and hence it does not form cyanohydrin. Now this hydrogen cyanide can also be obtained by reacting sodium cyanide or potassium cyanide with a strong acid. For example, with HCl, it gives HCN plus a sodium chloride. And once this hydrogen cyanide is produced, it can react with aldehyde ketones to form a cyanohydrin. One more example. Now we are reacting this with sodium cyanide in the presence of HCl. Now the question is, what is the product form? Now if you look at the reaction, sodium cyanide combines with hydrogen chloride to first give hydrogen cyanide, then hydrogen cyanide adds across the aldehyde to form cyanohydrin. So the product of this reaction is this is a product of this reaction. So this is the reaction of aldehyde ketones with hydrogen cyanide to form cyanohydrin. But remember, ketones are less reactive than aldehyde towards nucleophilic addition reactions. Now second reaction is with sodium hydrogen sulfite. and sodium hydrogen sulfide formula is NaHSO3. Again, aldehydes are more reactive than ketones towards sodium hydrogen sulfide. Now, this is a reaction given. This is our carbonyl group. Now, first step is addition reaction with sodium hydrogen sulfide to give this addition product. But in this product, you have a very strong base alkoxide anion present. You also have a sulfonic acid group present. So what happens? The transfer of H plus ion takes place from the sulfonic acid group to alkoxide anion. So the second step is H plus ion transfer, and it results in the formation of this crystalline product. This product is called a crystalline product. And this product is soluble in water, and as a result the equilibrium shift in the forward direction. Now we take one example. Now suppose you are given this formaldehyde. So formaldehyde on reaction with NaHSO3 give this addition product, and then transfer of H plus ion takes place. Gives this crystalline product. And the formation of this crystalline product is also used as a test for aldehyde and ketones. And this crystalline product, now this crystalline product can be converted back into parent aldehyde and ketones by using hydrochloric acid. So this crystalline product can be decomposed by hydrochloric acid with the liberation of SO2 gas. This reaction of aldehyde ketones with the sodium hydrogen sulfide can be used as a test to identify aldehyde ketone, also used in the purification of aldehyde and ketones, and also used in the separation of aldehyde and ketones from other compounds. Now the third reaction is a reaction with alcohols. But aldehyde and ketones reacts only with primary alcohols, and the reason is that primary alcohols are the most acidic in nature. They can easily provide H plus ion. So this is the reaction of carbonyl group with alcohol. Now this is an example of a monohydric alcohol, as you have only one OH group present. And the reaction takes place in acidic medium. So we use a hydrogen chloride as an acidic medium. So the addition takes place to give this is the first product. This is addition product, in which the alcohol and the alkoxy group both are present at the same carbon. Now this product is called hemiacetal. And this hemiacetal further reacts with the same alcohol and the same acidic medium and undergo dehydration to form a product which is called acetal. Now in acetal, the two alkoxy groups are present at the same carbon. This is called acetal. Now the first example is this. This is our formaldehyde. On reaction with methyl alcohol, in the presence of HCl, it gives a hemiacetal, which on further reaction with the same alcohol, methyl alcohol, same catalyst, hydrogen chloride, it gives acetal. Now, ketones are again less reactive towards addition reaction with alcohol than aldehydes. Now, next we will discuss the mechanism of this acetal formation. Now, this is our aldehyde, and the first step is the protonation of this carbonyl oxygen. This is called protonation. And second step is the nucleophilic attack of the alcohol at the carbonyl carbon. To give protonated hemiacetal. Followed by deprotonation, loss of H plus ion to give a hemiacetal. So, this is a mechanism of hemiacetal formation, and once the hemiacetal form, then it undergo dehydration with the second molecule of alcohol, and you already know the mechanism of dehydration of alcohol. Now, carbonyl group can also react with a dihydric alcohol to form cyclic acetals. And these cyclic acetals are highly stable, and as a result the equilibrium shift in the forward direction. Now, we take one example. This is our cyclic ketone, and this ketone is called a cyclopentanone. On reaction with ethylene glycol, in acidic medium gives a cyclic acetal. And the cyclic acetal is named as ethylene ketal of cyclopentanone. And this formation of cyclic acetal or cyclic ketal can also be used to block or protect the carbonyl group from the reactions. For example, if you are given this unsaturated aldehyde and you want to oxidize only the double bond without affecting the aldehyde, then you have to block the aldehyde group by forming this type of cyclic acetal. What we do, we first react this unsaturated aldehyde with ethylene glycol, it forms a cyclic acetal, and once you block this aldehyde, now you can perform any reaction of the double bond. So, what we do, we react this compound now with alkyl KMnO4, dilute alkyl KMnO4, and it oxidizes only the double bond to form diol. Now the fourth reaction is the reaction of aldehyde ketones with Grignard's reagent. Now this is also an example of a nucleophilic addition. Now this is our Grignard's reagent RMgX, and when RMgX reacts with formaldehyde followed by reaction with water in acidic medium, it gives a primary alcohol RCH2OH. This is called primary alcohol, 1 degree alcohol. And Grignard's reagent on reaction with any other aldehyde except formaldehyde and followed by hydrolysis it gives a 2 degree alcohol, secondary alcohol. And on reaction with ketones, RMgX gives a 3 degree alcohol. This is called 3 degree alcohol. Now we'll discuss one example. Now suppose our aim is to prepare this is called 2-phenyl butanol, 2-phenyl butane 2-ol from Grignard's reagent. So what combinations we can take? See, our aim is to prepare this 3 degree alcohol This is called 2-phenyl butane 2-ol. It's a 3 degree alcohol, and 3 degree alcohol you can prepare only by reacting the Grignard's reagent with ketone. So what combinations are possible? So we have 3 combinations possible. One combination is this. We are using phenyl magnesium bromide and reacting it with a butanone. Followed by hydrolysis gives 2-phenyl butane 2-ol. This is one combination. Second combination is we can take methyl magnesium bromide and reacting it with this ketone, aromatic ketone, this is second possibility. And the third possibility is using ethyl magnesium bromide and reacting it with the acetophenone. This is called acetophenone, followed by hydrolysis. So this 3 degree alcohol can be prepared by 3 different combinations. So that is the use of Grignard's reagent, but remember 3 degree alcohols you can prepare only by using Grignard's reagent. So this is all about the nucleophilic addition reactions of aldehyde and ketones.